when you have a Lagrangian and then you go to the Hamiltonian side, the conservation of the momentum is one of the equations, which is connected with mass and Weinstein reduction. Yeah, that's true. Yeah,
It's
sure.
not equivalent.
Yeah, sure. Yeah.
Another comment. When the hypothesis of equivariant action is important because, of course, it is true for the rotation group, but for the EV-top application. But for instance, the classical group of mechanics, Galileo's group, the action is not equivalent. So Euler equation must be modified. There is an extra term with linked to the symplectic class of cohomology.
That's probably closer to the symplectic formulation of mechanics or evolution system. But I mean, in this Lagrangian system, the Netter theorem, as I put it, whenever you have an invariant Lagrangian, this momentum map is equivalent always. But it's not symplectic. I mean, it's not, at least it's not written in the symplectic form. Yeah, I know what you are mentioning, which is very important, but it's not strictly what I have here. Yeah, thank you very much.
Other questions? No? Thank you.
Thank you very much. Yeah, I took quite a bit, so this is raised because this go forward, backward, and this on the top is the pointer.
Okay.
So the last speaker of the session is Paul Bergold from Surrey. He will present Madelung transform and variational approaches beyond Born Oppenheimer molecular dynamics.
Thank you very much. First of all, I would like to thank the organizers for the successful conference and for giving me the opportunity to present this work. So as maybe some of you have noticed, there is a slight change in the title as compared to the GSI paper, where we basically analyze how Born Oppenheimer molecular dynamics arises from asymptotic expansions on the level of the Lagrangian. And in this context, we present two particle methods. One is a fully quantum particle method, which is called the Bohmian method. A second one is a mixed quantum classical trajectory-based method, which is called the Koopmans method. And since we have made good progress with the numerics for the Koopmans method, I have decided that I put the focus on the Koopmans in this talk. And I would also like to emphasize that this is joint work with my supervisor at Surrey, Cesare Tronci, and Werner Bauer, also from Surrey, François Gelbama, who is here, and Daryl Home from Imperial. So let me start with a quick motivation of mixed quantum classical models. And those of you who attended the talk of Cesare in the afternoon already saw a bit of this. So of course there are many ways to motivate mixed quantum classical models, but here I focus on two of them. First of all, mixed quantum classical methods can be used to address fundamental questions in physics. On the other hand side, and this is something which is maybe more related to the talk I'm giving here, is to overcome the curse of dimensionality, at least to some extent. For example, if we think about many-body quantum systems, if we think about molecular dynamics, sometimes it's just too costly to solve the full Schrödinger equation, and therefore we have to come up with methods that, break the curse of dimensionality in some sense. And one of the state-of-the-art methods to do this is called Born Oppenheimer molecular dynamics. So this is a very famous ansatz, basically, where in a molecule the much heavier nuclei are modeled as classical particles, and we retain a fully quantum descriptions for the electrons. And of course, this is sometimes not enough, and we aim for building a model which goes beyond Born Oppenheimer molecular dynamics. And the new hybrid model, which I present here, is basically based on a geometric approach that has helped, on the one hand side, to overcome long-standing consistency issues, and on the other hand side, to design a numerical method, the Koopmans method, which has useful features. And when I say useful features, I'm referring to the underlying Hamiltonian structure, which is favorable for the numerical implementation, as we have conservation properties. Good, so let me say a few words about the construction and the geometry of that hybrid model. First of all, it is important to emphasize that this hybrid model is based on a wave function description. More precisely, it's based on so-called Koopman wave functions. And before we start to talk about hybrid wave functions, we better understand how classical dynamics can be formulated as a unitary flow on a Hilbert space. And the connection is basically made by the so-called Koopman-von Hoof equation, which is written here. And solutions of the Koopman-von Hoof equation return classical dynamics for this phase-space density here. And I also refer to the paper of Cesare and François, where all of this is worked out in detail. So the question is, once we are equipped with a wave function in classical space for classical dynamics, how can we derive a mixed quantum classical or a hybrid model? And the way the authors worked, so this goes back to a paper in 2019 by Bondar, Gelbermar, and Tronchi. The authors derived basically a quantum classical wave equation which was based on a partial quantization of a two-particle classical wave function. And this eventually leads to this type of quantum classical wave equation, where our epsilon here is a hybrid wave function, which is, as we know from quantum mechanics, a square integrable function, but now both in the classical and the quantum coordinates. Right? So this is a wave function, a linear model, and by noting that the right-hand side of the this wave equation here is given by the action of a Hermitian operator, we see a similarity to usual Schrödinger dynamics, right? So this is basically the same form as we know it from the Schrödinger equation, and therefore we also see immediately that we have an underlying action principle, which is of Dirac-Frenkel type, and it's written down here. So what was the new news, and why is it not enough to end here? On the one hand side, and this is an important result, we can see that we obtain a positive definite quantum density operator, which is given as this. However, it is still unknown if that linear model, so the quantum classical wave equation, does account for a positive definite classical density in general. So for specific systems, the authors were able to show it, but in general it's not known. And since this is a crucial point, Cesare also mentioned this because of consistency issues. The aim was to work harder using geometry and following hints of George Sudarshan, who basically started in 1976. And the way they worked was to combine Lagrangian trajectories on the classical phase space with a gauge principle which yields a sign-preserving transport equation. And for now, maybe this is just can be seen as a side product. This ensures that classical phases do not contribute to measurable expectation values. So here I just give a short overview of what was done for the derivation of the new nonlinear hybrid model, which was presented in the paper 2022 by François and Cesare. So there are a few steps which are important. So on the one hand side, what is done is they use two important transformations. The first one is the so-called exact factorization. This is needed because if we think of a hybrid wave function, we basically want to know which part of the wave function describes the classical part, which of it describes the quantum part, and this is achieved by performing the so-called exact factorization, which is known from quantum chemistry. And on the other hand side, they performed a Madelung transform for the classical part in order to isolate basically the classical phase, and that hydrodynamic formulation then allowed to take advantage of Lagrangian paths, which later identify the Koopmans trajectories, in general trajectories, but for these models, it's the Koopman trajectories. Good, so they also derived the phase invariant variational principle by noting that the classical density evolves by a push forward of the initial condition by a Lagrangian path, and performed Euler-Poincaré reduction. And the resulting equations of the nonlinear hybrid model are presented here, and because of the time constraint, I don't want to go too much in detail, but just emphasize a few points. So first of all, so this is the nonlinear model where the vector field X and this calligraphic Hamiltonian is given like here. We have an underlying Hamiltonian structure. Secondly, we have an H-bar correction to the Ehrenfest model. So by skipping the H-bar terms here, we just remain with these blue parts. And this is a well-known model. It is known in quantum chemistry as the Ehrenfest model. So this was an important result. So we can see this is something which is an extension basically of the Ehrenfest model. And then this is something which was presented in the GSI paper, the connection to molecular dynamics. So in the classical limit, so if we think of a large electron, nuclear to electron mass ratio, or a small electron to nuclear mass ratio, and one can show that basically one recovers a phase-space formulation of the Born Oppenheimer molecular dynamics equations, and which is basically a Newton's law for the electron, for the nuclei, and a eigenvalue problem for the electrons. And one thing, I mean, just by looking at the equations, we can see that this is a beast in some sense, so it is hard to find solutions on the level of the PDE. So the system is hardly trackable, and we need a closure to find basically, or to find the numerical algorithms. However, we can see that the Poisson brackets, which appear here, they prevent gradients, so they produce gradients, and these gradients in the equations does not allow for a trajectory-based closure, so singular solutions are not allowed by this model, so one has to go a step further, and so what was done, or what is done, is we perform a regularization, which was earlier done for the Bohmian method. So here the idea is, based on the Lagrangian, we identify the parts which are problematic, which prevent the particle-like solutions, and then we perform a smoothing of these parts, which eventually lead to a form of equations that allow for delta-like expressions. And these point trajectories are called the Koopmans. And it is important to understand that all of these modifications are performed on the level of the Lagrangian. So we retain the formalism and just replace the corresponding quantities in the Lagrangian. And so the question is, what is the connection now between this regularized Lagrangian, the corresponding equation, so to say, and the original model? And the regularization kernel comes with a positive length scale. We can think of a Gaussian kernel which has a variance alpha, and in the limit alpha to 0, we ask that kernel to tend to the delta distribution like a normalized kernel function, and therefore, in that limit alpha to 0, we recover the original Lagrangian, right? So that's the connection. The corresponding trajectory equations for the Koopmans method are found by replacing the ansatz, so these comps of delta functions, in the regularized Lagrangian here. And eventually we find this set of equations. So it's a rescaled Hamiltonian system for Q and P. We have this equation for the density matrix, and we have this Hamiltonian functional H, which is given here. So it comes with a mean field term and then an H bar corrections. And we can also see that there is a function AIB, which basically correlates all the different particles. And this function basically is given by a phase space integral over this Poisson bracket of the kernels and the Hamiltonian. And it carries this summation curve of the kernel functions in the denominator. And if we think again what the connection to the original model is, then we see that in that limit where the kernel function converges to the Dirac delta, we produce small values in the denominator, and this makes basically the computation of these integrals challenging, and that's basically the important thing which must be addressed in the numerical implementation. So this brings me to the numerical implementation. So for now we have to use a partial integration for the integrals, which is executed by a trapezoidal rule. And we also employ a time-dependent grid in phase space, which basically moves with the phase space distribution. For the time integration, we use a fourth-order Runge-Kutta method. In the future, we could improve both of them. For example, if Gaussian functions are used as the kernel functions, we could use Gauss-Hermite quadrature in the spatial domain and symplectic integrators for the time integration, which fit basically in the Hamiltonian structure. And for now, this is implemented in MATLAB. And I should also mention that provided that the kernel function in phase space can be decomposed into a product of a kernel in position and in momentum space, we are able to perform a partial parallelization of the code, which is not done yet, but this is something which can also be addressed in the future. So numerical results very quickly. So what do we look for? In the classical sector, we just visualize the time-evolved phase space density. In the quantum sector, we look for a measure of decoherence, which is given by quantum purity. So quantum purity is basically the trace of the squared of the density matrix rho here, and it is a measure of how mixed the quantum and the classical system is. And for the reference solution, we use a fully quantum solver for the Schrödinger equation, which is performed by a split operator Fourier transform method. And in the classical phase, in the classical space, we plot the Wigner distribution to compare. So the first result is the so-called Rabi Hamiltonian in the ultra-strong coupling regime. What is done here is we have a classical harmonic oscillator in the classical space, which is linearly coupled to a spin, and we also have a shift. The sigma x are the Pauli matrices, so the coupling constants are given here and the shift constant. So what we present here is results for 500 particles and an alpha parameter of 0.5. We have an initial shift in phase space and use a Gaussian shape for the initial wave packet, and in the quantum sector we use this density matrix. So these are the plots for the phase space distribution. So we can see on the left hand side is the reference solution, the fully quantum reference solution. The second one is the result for the Koopman method. this is the Ehrenfest result, which appears by dropping that h bar term. And this is the Bohmian method, which was also presented. It's a fully quantum trajectory-based model. And first of all, it is important to see that we have negative values in the Wigner distribution of the reference solution. Of course, this cannot occur here in the particle methods, but overall we can see that the shape of the wave packet is best produced or reproduced by the Koopmans here. By looking at the quantum domain, we plot purity, so we have the reference solution in red. I should also mention that the reference solution is going in a clockwise rotation, and we capture 5 oscillations of this oscillation in the time interval from 0 to 25. So as we can see in green, the Koopmans are able to reproduce these oscillations of the fully quantum reference solution the best, while in some sense the other particles methods get blurred out. And so the last result I want to present is a Tally-2 model. The Tally models are benchmark models which are used in quantum chemistry to basically model transition processes in molecules. There are 3 Tally models for different initial momenta. Here I present Tally-2 for the low momentum case, which is the more difficult case as compared to the high momentum. So for now, it's enough just to have a look at the corresponding potential energy surface. So you can think of a potential energy. We place a wave packet on one of these energy surfaces and give the wave packet a push, basically initial momentum, and then the wave packet travels near this crossing section. And when it arrives at the crossing section, depending on the speed of the wave packet, which we can control by the initial momentum, the wave packet starts to split, for example. So parts of the wave packet will jump to the lower part, and there are reflections depending on the initial condition. So this is important to model processes, as I said, in molecules. So here again we use 500 Koopmans, or 500 particles, the same alpha parameter, and now we initialize a wave packet in the upper part of the potential energy surface. Now I should also mention that the time scale is completely different, so we have to go 200 steps in atomic units. Delta T is 0.5, and this is the result in phase space. So we can see that basically all the models, as before, soft Koopmans, Ehrenfest, Bohmians, show the same behavior. But for the reference solution, we can see that there is a splitting of the wave packet. And by looking at the Koopmans, we can see that there is a splitting happening. However, the resolution of the number of particles is still too small, so we have to work on finding the optimal values of alpha and n. But what we can say is that something like wave packet splittings in general is captured efficiently, or let's say best, by the Koopmans method. In the quantum sector, we can see that we have the reference solution in red. The Koopmans solution lies in the middle of the fully quantum and the Ehrenfest solution. And one important thing before I close is to mention or to emphasize that this is a fully quantum reference solution. So we don't expect that basically the green curve should converge to the fully quantum solution, because it's a mixed quantum classical method. So we have to basically find out what the correct convergence is, what the correct values of purity and the phase space density is, and that is something which is basically ongoing work. Okay, so that's all I want to say, and thank you very much.
Some questions?
how the reference solution was obtained?
The reference solution is obtained by solving the corresponding fully quantum, for a fully quantum Hamiltonian, the Schrödinger equation, with a split operator Fourier transform method. So it's basically a splitting of the Hamiltonian and exploiting the fast Fourier transform. It's a highly accurate and fast solver, which is, I would say, state of the art and the most used reference solver in chemistry or for quantum dynamics.
Other questions? Yeah. You mentioned you had a moving mesh in the simulation.
Yeah,
right?
yeah.
I didn't get what you need the mesh for.
The mesh?
Yes.
So we have, by looking at these integrals, so we have basically at some point to compute integrals over phase space. And as you can see is that we have kernel functions which are localized for the given phase space coordinate. So if we have a coupon, right, it's a particle which has a q and a p, a momentum, a position and momentum, and these kernel functions are localized for each coupon. And what we can show is that by building that sum, that's what I meant with partial parallelization, you can basically just look for the integral. Of course, you cannot compute the full phase space integral. At some point, you have to truncate. And the way we truncate is basically in a localized area of the Gaussian distribution. And since we can do this for each coupon or for each particle, we ensure that the grids move with the particles because they are localized in the phase space points, right? So it's an adaptive grid which moves with the phase space density because the kernel functions are localized in these grid points set.
Maybe you must restart sometimes if the mesh would get too twisted, right? Is that possible?
So that's not the case for now. What we see is that, for example, if we have something like wave packet splitting, right, where parts of the fully wave packet go in different directions, obviously you don't have enough particles after the splitting and the resolution gets bad. So you need higher numbers of particles if you see splitting something like this. And also it's clear that, oh sorry, wrong direction. If you look at the fine structure which is in the reference solution, right? So in the Wigner distribution, now in phase space, you can see that you need high number of particles to resolve basically these fine structures in the wave packet in the classical density. So yeah, and for now that's basically the work to find out what is the correct alpha parameter, which is in some sense model dependent, and also to find a good number of particles. Of course, it should be a small number because this is what you want. And yeah, for these numbers, we can see that already we can outperform in some sense the other particle methods and capture effects which go beyond Ehrenfest dynamics. That's the important take-home message. So this model can capture effects in the quantum and in the classical space for given Hamiltonians which go beyond Ehrenfest dynamics. Yeah.
Other questions?
So maybe just a comment when you have purity, when you have the definition of purity, right? So maybe you need to clarify, right? Because
This one?
you're right. So
Yeah.
if rho is a projection, then
Oh, sorry. Yeah, no. This was actually stupid. If rho is a projection, then it's just one. Sorry. So rho is just a density matrix in general. So basically, this shows if we can write rho as a projection, then the purity is 1, right? But as soon as you cannot decompose the density matrix, you have values which are basically so the time evolution of purity is non-trivial. You can say it like this, right? Yeah, but yeah, that's correct. It should just be the norm, basically the Frobenius norm of the density matrix squared. Yes. Other questions? Yes.
I have to ask, what about decoherence? Did you also measure the rate of decoherence?
Yeah, well, I mean, this is what we measure by quantum purity, right? So quantum purity is a measure for decoherence because it measures how mixed basically the quantum and the classical system is. We worked on different coherence measures. So what we can also do is basically to just plot the off-diagonal elements of the density matrix. But as I said earlier this day, it might be problematic because sometimes people use base-dependent definitions of coherence, and this is a base-independent definition. So whatever you use for decoherence, the measure, it should be consistent. And using a base-dependent definition is sometimes misleading. So for now, this is just the way you plot, basically, right? Yeah, but off-diagonal elements of the density matrix would also give you a measure of decoherence, right? So how the population in the off-diagonal elements happen.
More questions? If not, let's thank Paul again. Thank you for coming.
Merci pour l'attention.
The second group picture has been postponed tomorrow because we have a Clement weather tomorrow. Because of us.
Am Anfang?
Ja.
Okay, das war Anfang. Ach so, das da. Ja, also das ist wie gesagt, dieses Y hier ist keine normale Quantenfunktion. Also das hängt eben auch jetzt von klassischen Variablen. Du hast quasi in einer vollen Quantensimulation hast du eine Wellfunktion Und das Argument der Wellenfunktion ist das Element, über das man integriert im Mittelraum. Ja? Und das ist quasi eine vollständige Wellenfunktion. Ja? Ist es anders. Y hängt eben auch noch von den klassischen Komponenten ab. Ja, das ist übrigens auch der Grund, warum du den Quantenanteil bekommst, indem du quasi die klassischen Anteile rausintegrierst. Also du machst quasi sowas wie eine Projection. Wenn du das quasi für diese Anteile integrierst. Ja? Und das gibt dann den Quantenanteil, genauso kannst du von dem Y auch